Good morning, class. This is Null instructor. Today I'm going to be discussing a few questions with you. That is a trail from the last lecture that we conducted. Now we have a few questions that would basically need some practice regarding the questions of probability. Now the first thing that you should understand is that how to apply probability. That is the main concept behind the possibility that you're going to check the outcomes and the chance claims out of which you can actually draw conclusions. So now, for instance, we have this practical demonstration where there are two kinds of dice with us. One is the red one and the other is the green one. You see, the one is the red one. This question basically 23 to 30 of exercise section 7.2 in case it's not that clear to you. Now in this they're asking us that the numbers, okay, so I'm going to be writing various possibilities that are there, which are the, if you recall, events. So first let us just consider that A in this case is a red die that shows 1. So I'm going to be drawing the sample space for this. So now if the die is 1, so either you keep the die as the left side or the right hand side, right? So if it is the left or the right, in that case it's going to be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. Okay? This is going to remain constant because we can't really have, this convert. We could also have 6, 1, 5, 1, but then that would not be the red die, that would be the green die in this case. So now this part is clear. Well, let's just have the other event. It says the numbers add to 4. Okay. So now you see that the numbers 1, 3, I can just pick 1 from here. Then I would also know that this is also adding to 4. Now you have to draw the whole sample space of 6 into 6 equal to 36 possibilities for rolling the two dice that I discussed just in the previous lecture. And which other, if I say 3, 1, okay, then 4, 1 cannot be anything starting with 4 cannot be, summing to 4 because 4, 1 would be 5 actually. So I have to have a number which would be lower than 4. In that case, there was 3, 1 and 1, 3, and then there is also 2. So in this case, I can have 2, 2. That would be completing my event for set or event B as the the requirement for part on second event in this case. Now let's just move on to the third one, which is C. At least one of the numbers is 1. So C says at least one of the numbers is 1. So again, as you can see, it says 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, then 1, 6. I can have 1, 6 here. Then I can have 6, 1, 5, 1, because they say that at least one of the numbers is 1. So 5, 1, 4, 1, 3, 1, 2, 1, and 1, 1 we have already written, so you can just see how many possibilities that will come. Similarly, we have D. Now, D says the numbers do not add to 11. In this case, the numbers, okay, so I'm going to be taking advantage of the concept of complement. Now, the complementarity means that anything which is the opposite, if it is easier to calculate, we would be finding that out and subtracting from 1, because as I said that this thing would actually be equal to probability of 8. It's the rule for complements. Now, one of the examples I can give you is head or tail. So it's 50-50 chance of occurrence of both. So in that case, I have probability of head is 1 minus probability of the second event, which is tail, which is again, so in this case, it will be 1 minus 0.5 and is equal to 0.5. So that means that 1 would be actually addition of both, complement plus the opposite of complement in this case. So now when they say that the numbers do not add to 11, there are many numbers which do not add to 11. So let's see those numbers which actually add to 11. In this case we have what? 5, 6 adds to 11, 6, 5 that adds to 11. So out of the sample space of 36, if I subtract two possibilities, I get 34. So now I know that 34 are the numbers or the possibilities that can arise out of this solution when we want that they should not add to 11. All these numbers do not add to 11 except 5, 6. So now I need to have something in this case where I have to narrate all these up to all the numbers which are not included in this. So this is basically ND would be 34. So you can just have all the numbers from 1, 1 to minus the D complement. So in this case the D complement would be 5, 6 and 6, 5. So anything subtracting the entire sample space, actually this is the entire sample space. Entire sample space minus the D complement, which is when they are, I'm going to also be writing the B complement here. So now B complement in this case would be the numbers that do not add to 4. So if you can see that the ones that do not add to 4 would be 36 minus 3 in this case would be 33, right? So now we have the B complement, we have the D complement, and we have the B. Now let's just come to the problems. They say now in question number 23, the red die shows 1 and the numbers add to 4. Okay, so I told you that when we have a union, we have OR. If we have intersection, we have an AND. So when the red die shows 1, we have all these possibilities and the numbers add to 4. So in this case, there will be just one that I'm going to be isolating. There's only one common. So I can have A intersection of B in this case. Intersection of B would be 1, 3. Okay? So A intersection would be 1, 3. Now, next part, question 24 says that the red die shows 1, but the numbers do not add to 11. Okay. The red die shows 1. So I think they are basically talking about the D part where they do not add to 11. So this is the entire sample space, and the red die shows 1. And in this case, now, as you can see, all these numbers would be the red die that shows 1. So I'm going to be having again intersection of A with intersection of D. So in that case, our entire sample space will be consisting of all these possibilities. So in this case, N would be 6. You can just rewrite this entire thing, which is actually A, okay, which is equal to A. Let me just write this again. Equal to A. Because I need to have something in common. Because if I'm having intersection would mean that you need to find out the commonality between both the events. So in this case, I can have all the 6 possibilities because they are not equal to 11 and they are all in A available. So the part 25 is about not adding to 4. So this would be, I think, again, I've already found that by chance. You see, this is adding to 4. So if something is not adding to 4, it will be the complement. 36 for the total possibilities minus the B portion would give you B complement. Okay, so now the next part is the numbers add to 11, already done here. The numbers add to 11, and there's the B complement where I've restricted. Now the numbers do not add to 4, this is part 27. I hope that you can do the next 2 parts at least. The numbers do not add to 4, but they do add to 11. Okay, so I have the complement here. Now I'm going to be having an intersection here. So the numbers that do not add to 4 are this entire sample space. Okay, I have B complement, intersection D complement in this case. And that would be entire D complement is equal to B complement. because this is a larger sample space where they are not adding to 4. So I can have all these values which are not these values, okay? So I can have an intersection where, you know, because you see, 1, 3, 3, 1, 2, 2, they were subtracted from this entire sample space. So I can have the entire sample space, but I need to have something in common with something which is adding to 11. So in this case, there are 2 possibilities that add to 11, and that is just basically out of 33 possibilities, these 2 would be the common, and that would be D complement. In this case, they are just 2. In this case, n of B complement to B complement would be 2. Okay. Now you can do 28, 29 for practice, and I'm going towards part this one. This is 30th question. It says that either the numbers add to 4, or they add to 11, or at least one of them is 1. Now you can see that they have used the word or. Now this or means that it's a union, okay? Because union is something which would actually increase your samples. Not the sample space, the possibilities that you're taking would increase the event actually in size. Intersection would actually be the subset, but the union would actually increase, would be more than actually one possibility or either of the possibilities in this case. So they add to 4. This is probability of B. This is going to be B. Then, or they add to 11. This is going to be D complement. So I'm going to be saying union of D complement, or at least one of them is 1. So now one of them is 1 is basically 11 possibilities. As you can see, 6 of these and 5 that I have already calculated for C. And now how come I can just have this entire one? So this is 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. You can just see the 6. And you can see these 5. So total in 11. So I can say that, or at least one of them is 1. This is C. So for the union of these is going to give you how many possibilities in this case? N of B union B complement. And remember that while you are finding out the possibilities, there will be some repetition. Because what is there would be in B as well. As you can see, 1, 3 is in B, 3, 1 is in B. So you can't repeat what is common. So that means the rule would say that when you are having, actually the rule says that if there is a union between 2, then that would be B plus D complement minus, B intersection D complement. So you're going to be taking out the, whatever is common between them and minus B intersection C complement in this case. So whatever is common between B and C and D complement, you are just going to be writing it one time and not twice. Since there is nothing common with D complement, so in this case you are going to be subtracting with B intersection C. What is common between this? Now B and C has something in common. So once you write all these, you're not going to be rewriting them, right? So now how many do we have? 3, 4, 5, 6, 7, 8, 9, 10, 11. So in this case it's going to be, they add to 4, so this is 3 possibilities in this case. They are adding to 4. So now again we have how many of these? Or they add to 11. Okay, I have 2 here, 5. And C is basically that at least one of them is 1. So this is basically 3, 11. So this becomes overall 16 minus whatever is the intersection in this case. So what is the intersection? Now you can see that we don't have 2, 2 here. But we have 3, 1 and 1, 3, which is the common one. 1, 3 and 3, 1. So whatever is the intersection, I am going to be, let me just highlight it with a blue marker so you can see this, this, this and this is the intersection. So I'm going to be subtracting 2 from this and I get 14 outcome. Okay, so this is all about union, intersection. Mutually exclusive is the next part that I would like you to understand. And before that, okay, so there's another concept which is okay, let me just go to it first. This is about combinations. So now what is the combination? Let's just look at a question just pertaining to combinations. Okay, this question is basically symbology, where it says that a packet of gummy candy contains 4 strawberry gums, 4 lime gums, 2 black currant gums, and 2 orange gums. This is question 19, section 7.2. April May sticks her hand and selects 4 at random. I told you that for combination you need to have something selected at random, but if it has order, then it would be permutation. Complete the following sentence. The sample space is the set of, okay, the sample space is the set of all possibilities arising out of these sets of 4 strawberry gums, lime gums, 2 black currant gums, and 2 orange gums. So all these possibilities is a sample space. Now, the next part says that found a combination of 2 strawberry and 2 black currant gums, and when that April will get the combination she desires, the set of all sets of 2 strawberries out of the 4 strawberry gums. So it's going to be a set of all sets of 4 strawberry gums and 2 black currant gums. So so the combination would actually include out of the possibilities of 4 strawberry gums and 2 black currant gums. Then she can have 2 at a time drawn for strawberry gums, and then 2 for black currant gums. This is how you explain is the set of all sets of strawberry gums and black currant gums. Now this is a theoretical part. I would like to go towards something which is more practical. Let's just see. Okay, so this is one question. It talks about combination. Okay guys, this is about, how many outcomes are there in the sample space if Pavlov randomly picks 3 marbles from a bank of 8 marbles? Okay, in your book, the notation is not at the moment used for combination because probably they are not particularly focusing on combination. However, I just want to use this combination. You are free to use the one in the book or this one. For opening of the combination, you basically have to go backwards 3 times because this is at least 3 draws from a random of 8. 4 red ones, 2 green ones. So 4 is the red ones, 2 green ones, and 2 yellow ones. Okay, and this is the 3 draws. Now I can have this factorial open as well, but you know that this is cancelled, so the outcome would be 56 in this case. Similarly, we have the second part of this in the first section 39. How many outcomes are there in the event that none of the marbles he picks are red? Okay, so if none of the marbles he picks are red, would be 8 minus 4, and still he's drawing 3 out of this. So in this case, it would be 4 into 3 into 2 into 3 into 2, because 1 is known to be constant. Now I'm going to be deducting this cancelled. Okay, so the outcome is actually 4. Not deducting, sorry, it's just cancelled. We're having the 4 as the possible solution for the set, or the number of combinations can be 4 in this case. So how many outcomes are there in the sample space? Again, question 40, it would, how many outcomes? 56. And then it says, in the event that all marbles he picks are red. Okay, so in that case again would have the same answer, because if all the ones he picks are red, would mean that, okay, now there is something different about this one. In the sense that if you want to isolate the red ones again, I can use the complement formula for this. In this case, I subtracted the red one because I was interested in the 2 other ones. But now I want the red ones, so how to subtract the 2 other ones? This is the probability for the 2 other ones. So for red ones, I can just simply say it's 56 minus 4 is 52. That should be for the red ones, correct? Again, just using, this is for green plus yellow, so now this is for red ones. subtracted from the total sample space. Now, this is actually the total sample space, NS. Now, how many outcomes are there in the event that Pablo picks one marble of each color? Okay, sometimes we can subtract, sometimes we can isolate, and sometimes we can have multiple solutions for different combinations. He's saying that he picks one marble of each color. In that case, would be out of 4, he picks 1. Out of 2 green, he picks 1. Out of 2 yellow, he picks 1. So in this case, for 2, this is 1 factorial is 4 into 2 is 16. So that should be the solution for in this case. You are going to multiply these possibilities, okay? Because this is just the number of combinations for, like I said, the possibility for having a head and a tail. So you just have to see when for combinations, when you're drawing something from a large sample space, you simply multiply. The part 42 says how many outcomes are there in the event that the marble Pablo picks are not all the same color. Okay, so if they are not of the same color, so now I leave this to you. They are not of the same color, so that means he has to pick all 3, right? So now you have to check whether any of this can be used for this technique, and I hope that you can do it and come back to me if you have any confusion. Similarly, I have to go for a practical application at this moment. Let's just look at the last application, then we'll move on to the next section. Okay, so now, there are a couple of questions. Let me just read the housing prices. From 43 to 48 exercise, they're based on the map below. They've shown you a map, okay? Shown you a map, and it says that the percentage change in housing prices from 2014 to June 2015 in each of 9 regions. So they have given you 9 regions. I hope you can see this clearly. This is Pacific, Mountain, West North Central, West South Central. Then we have East South, East North, South Atlantic, Middle Atlantic, and New England in this case. So if I want to have the map with me, then I can see based on the percentages that are given, I can draw conclusions as per the requirement of the question. Okay, so now these are the housing prices in percentages, and what are they asking? I'm just going to be doing one part, and then you can just look at other parts. Okay, let me just do the last part where they just put a yellow arrow. Okay, so this is perhaps more advanced than the others. It says that you are choosing a region of the country to move to. So you're going to be immigrating, relocating to that place. In which of the following pairs of events are mutually exclusive? Okay, the concept of mutually exclusive means that you are to make 2 events independent of each other. So that is, the result of one would not be affected by the other. And if they are not mutually exclusive, that means that they're dependent in some way. So we are going to be studying this concept in the when we do actually the conditional probability. That will be next week. Now it says which of the pairs are mutually exclusive. So you have to tell of the choices that they've given to you, which of these choices are mutually exclusive if you're talking in terms of pairs. So let me just see what is the outcome for event A. In this case, event A is you choose a region from among the 3 with the least increase in housing prices. So you choose 3 options with the least increase in housing prices. So if you see this, which one do you see the least in housing prices? And this is event E. So if I look at event E, okay, I have to rub this one. Now, if you can see that the least increase is, I can isolate this event as Middle Atlantic, which has 1.72. Then New England, NE for New England, which is 3.18 in this case. Then I have West and North Central, which is 3.91. West North Central 3.91 as the total sample space for event E. Again, now what I have asked is, I have to just go back to part A. You choose a region from among the central divisions. Now I have to select a region from central divisions. Okay, so now this was New England. So central would be something like this. This would be the central part, with west, north, central. So F event in this case would be west, north, central, west, south, central. Now in this case, we are not considering whether it's the least increase in housing prices. We're just considering the options of the central area in the map. So now east, north, central, and we have east, south, central. East, south, central. Okay. So now I have to decide whether all these pair is mutually exclusive or not. Whether it's not mutually exclusive or not. So can I have something in common? Okay, so there's an intersection which is possible. If intersection is possible, then this is not mutually exclusive. Not mutually exclusive. Now let's just look at, this was part A. Now I have to look at part B. What does part B requires us to do? Part B says, you choose a region from among the three with the least increase in housing prices. Okay, that would be the same as event A. And F says that you choose a region on the east or west coast. Okay, so now you know that we have west, we have east, and we have Pacific in one side, and we have New England, Mid-Atlantic, and South Atlantic on the other side. So if I were to draw sample space for part B, F, which is Pacific, okay. Then we have New England, then we have Mid-Atlantic, and we have South Atlantic, all this portion, leaving aside the central part, South Atlantic. Can I have an intersection? Okay, so intersection is possible with N, A, although, okay, we can have two in fact. So naturally then this means that this pair is not mutually exclusive. Because there is an intersection which is possible. Had it been mutually exclusive, these two would have had different answers altogether. I'm going to be moving on to the next section now, which is section 7.3. Okay, so now I hope that, I think this is section 7.2 or 1. Okay guys, I think, sorry, this is section 7.1 and it's not section 7.2. And we have section 7.2 is about relative frequency. You can study that. I've already discussed this concept in the previous lecture. Now I'm moving on to section 7.3. This is pretty easy. It's all about frequency expressed in terms of the total sample space as a vulgar fraction. This is probability and probability models. Okay, now let me just first of all make you understand what is probability model. Now we have actually done all this in terms of when I was explaining to you how you're supposed to, have a sample event, sample space, which would be S, then an event which could be A or B. We just did E and F, which could be the whole sample space was all the regions in the map, I suppose. And then we have all the outcomes. So if the outcomes are expressed in terms of each outcome as a percentage of the sample space, then that would be the probability. The probability has to be expressed like the relative frequency. It has to be expressed in terms of a fraction. So now let's suppose they have given you a sample space with a lot of possibilities, and it can have between 0 to 1. Okay, the possibility has to be between 0 to 1, like I just gave you an example of all the solution sets of rolling a die from 1, 2, 3, 4, 5, 6. So now you know that all these outcomes are total 6, and occurrence of each is actually 1 by 6. You can't just say the second is occurring 2 by 6 times. No. The probability would be again 1 by 6 for each. So in the end, it would be 6 by 6. If you add all of them, it would be 1. That is the probability would be 1. Because see, this would be 1 by 6 plus 1 by 6 plus 1 by 6. 1 by 6 would be 6 by 6. Okay. So then we have 1. You can have 0.5 plus 0.5, half plus half as 1. It always is equal to 1. Then let me just. Okay, so now if you look at this, they've given you almost head and tail. We've done enough of head and tail though. We have outcomes and the probabilities, and you just add those. Okay, now if they ask you of the probabilities of occurrence of 1 and 6, so you can just maybe draw a table like this and then add each. Okay, so 0.1. If they're giving you a probability of something that maybe it is some kind of a crooked die, that they have some probability that this event would come more than often than the other one. So you have a probability which is 0 for this case, and then you can just simply add. If question gives you a delta something like that, then you can just simply say that all these will be giving you 0.3, and probability of 3 in this case is 0. Then why it would be is that we have some distribution is given to us, and these numbers can be between 0 to 1 in this case. Then if it is totally uncrooked fair die, then we can have all these equal possibilities. Okay, so you can just look at these examples with head and tail. I think I have drawn that in the first lecture. I've already done that for you. So each possibility would be 1 by 36. If you want to have a solid event where each possibility would be out of 36, could be 1 by 36 in this case. So you can just have 1 by 9, just add them up, total probability. And it is actually, like I told you, each event by sample space, each event by sample space. So they said the roll of fair die. Why they use this word? It means that it has to be unbiased die. And I do this also the pre of 3 times tossing of head and tail, and you get 3 by 8. Okay, this one is a bit important because we have vehicles where it's 1.9 million hybrid vehicles, and had been sold in the United States through October of 2011. And all these 955,000 were Toyota Prius, 205,000 were Honda Civics, 170,000 were Toyota Camrys, 105,000 were Ford Escapes, and the rest were other makes. What is the probability that a random selected hybrid vehicle sold was either a Prius or a Honda Civic in this case? So now, first of all, you need to know what is the possibility for the entire sample space is 1.9. Was either a Toyota Prius, but it was not a Camry. So we have to subtract the Camry from the entire sample space. So first of all, you calculate what is Toyota Prius. 205,000 by 1.9 million. Then we can have Honda Civic 170,000 by 1.9 million. And then, or we can just subtract the Toyota Camrys out of it. 170,000 is for Toyota Camry. So Honda's 205,000 is for Honda Civics, and 955 are Toyota Prius. So we have 205, 955 by 1.9 million, and 205 by 1.9 million. But we will not have 170,000 for Toyota Camrys in this case, or Ford Escapes. So now you can see that this is the set of sold total set, where we can add 955, or we can just simply independently, we will not be adding those of the for Toyota. Which one is that? Toyota Camrys. We won't be adding for Toyota Camrys, just be for Pri and Civics. So as you can see, this is 116 by, it's the total figure for all. Just add it up. Now the next part, they say this event consists of those hybrid vehicles sold that were not Camrys. It's a very easy complement process here. We have the total sample space of 1.9 million. Subtract the Camrys, which is 170,000 in this case. This is 170,000 in this case. So we'll subtract from the total sample space. And then we can just actually divide that by the total sample space. So you can see that this is 0.91. Okay, let's just move on to indistinguishable dyes. So there are two kinds of dyes, guys. We have indistinguishable and the distinguishable ones. If it is indistinguishable, it would mean that both either of the same color. You can't really distinguish between both of them. And if it is distinguishable, you know it's either red or green or blue and white, whatever colors of the dye. You can just make them out separately. And you can just recall, just do this. I think we've done enough of this. Okay, this is a beautiful picture. They're actually giving you the possibility of all this. So if you have one event as 1 by 36, if you have 1, 2, 2, 1 out of the sample space, you can have 2 by 36, which can be simplified to a vulgar fraction of 1 by 18. Now, this is similar concept if you are given a set of possibilities, and if you do not have 1 as x, so you can just simply subtract all of these 6 by 6, minus 1 by 6, minus 1 by 6, and minus 1 by 6. So again, this was 3, 4, and you can just have 1 by 6 and 3, 4, 5, 6. So keep subtracting out of this 1, 1, 2, 3, 4, 5. So when you subtract this, you can have this x value. This is the concept. You can have all these equal to 1. This is 5 times y, and then you can have an x. So you can have x value, you can just have one known, but not two unknowns. So how come is this possible? So they're just giving you a possibility where they have probability distributions, and one could be termed as x. So you can just, out of, because the sum would be actually 3, 4, 5, 6, 7, 8. So out of this 8, which is actually 1 minus all of these except for the one that we want to find out. So this is if they ask you to also calculate only the separated isolated events of 2, 4, 6, you simply add them up. But if they ask you to, for these possibilities to occur together, then you just simply would be multiplying them if there's something common between them. I want to show you an example. Okay, so there are a couple of principles that we also want to do. So we have an additional principle in this case. I'm going to go it over. Now, and we have two events, okay? I've already shown you this one. But when we talk about this as a null set, it means that there's nothing in common between them, okay? So there's nothing in common, then you can just have 2 as this, and you can just simply add them up. Okay, so this is just giving you an example of what is an intersection, what is a union, and they've given you an example of a rain. So 10% chance of raining, and 20% chance of high winds, 5% chance of both. So that means that then you can isolate, then you have to subtract this. To do these examples, there are some principles again. I would want you to know that PS is 1, just probability of something happening. Okay, so this concept is basically based on the concept that PS can never be null set because there always has to be something happening. You can't just say that there's nothing happening. Okay, even if the environment, there's no rain in the environment, it's cloudy or whatever, then you can just say that it's cloudy. You can't just say that there's nothing happening here. And now null set is 0, that is the probability of nothing happening is 0 in this case. This is how you interpret this. You can't just say that there's nothing in the air. Complement, I've already explained to you what is complement, and sum of both complement and the opposite of it is equal to 1. And then you have if it is chance of rain tomorrow, then what is the chance it's not going to rain? We subtract the chance of raining. You get this value. Okay, so now they have explained one principle to you, which is rather easier because you already know that the intersection in this case would be 0. Null, we have already explained, is 0. But we want to know if there is a union of sample space and null set. So what do you get? Obviously, with null set, you subtract sample space from both sides of this union. If this is a union, so you have PS plus, so this is actually PS plus P of this minus PS and is equal to PS minus PS. So in this case, it would be cancelled. So you can say that P of this is equal to 0. Again, the concept is that the probability that nothing is happening is equal to 0. Similarly, we have intersection of this, union of this is possible, but intersection would give us a null, but a union would give us the entire sample space. In this case, this and this added. But you can always have the complement as, because this is this entire sample space, and we can say that this is equal to 1. So 1 would be the opposite of, 1 would have either the opposites of both sides to have the complement value secluded. Okay, so now we have this example where we have this is an interesting example. So again, they have told you that there's a probability that a random selected subprime, okay, there's a difference between a prime, which is a high quality loan, and a subprime, which is a low quality loan. Home mortgage in California was not current, was 0.51. So in this case, as you can see, if something which is not current is either it's a C complement or a C. So if it is a C complement, then you can have a C as 1 minus 0.51, which is 0.49. So that means something which is current is 0.49, but not current is 0.51. Now the probability that a mortgage was not current, which is complement in this case, it is not current, but neither in foreclosure nor repossessed, was 0.28. So that means that if it is not current, is actually neither in foreclosure nor in foreclosure. That means there has to be something which is in foreclosure, but it could be non-current. So we would be having an x and a value of 0.28, and this is going to be 0.51. It's very simple. Just subtract 0.51 and minus 0.28, something like that, I think this. Let's just look at this. So yes, this is 0.51, 0.28, subtract and you get 0.23. A simple example in this case. Now again, in a very interesting example. So it's also, this concept is very familiar to you because I think I've discussed this, and when we were doing intersection concepts, just revisit my last lecture and discussing section 7.1. But now this is just gone one step beyond. They ask you that if it is 695 million items are sold, this is the total of 695 million items. We have Mac, iPhone, iPad, and we have number of years. You have to find out whether it's a Mac first of all. So this is perhaps event A. So this is A. So the Mac is 53 by 695. So I can just simply write 53 by 695 is the event A. This is the probability of event A now, because I have expressed it in terms of total. So now this is going to be by 695. Had I said just event A would have been 53. Now it was sold in 2013. Then I would be, basically what I would be doing is that isolating all the values here. So it's going to be 238. So 238 by 695. Okay. And then it is a Mac sold in 2013. Okay, so now we have a Mac plus 2013, so it would be, this one was just isolated to 16 by 69. It's a Mac sold in 2013. I think, yes, this was just 16 by 6, because this is just common list, this is intersection, sorry. So we would just be at the moment having this. So if it is a union, then we are going to be adding all the results. So we have 53 over 695 plus 238 by 695, and then we can subtract 16 by 695 for this part. But if it is not a map, so we can have the entire solution set minus map, which is again 53 in this case. So 53 can be subtracted from the entire solution set and then added back. Okay. So now let's just look at this example. When you subtract this value, then you can just simply 695 minus 53, and then you can just have then divided by the total sample space. Okay, so they have given it to you in great detail here. They have solved each and every value here. Now as you can see that this is probability either two-way, and then you can just simply have an intersection of subtracting it when you want to find out the union of either of these two. Okay? So now, and the last event is then, again I told you that this is probability which is 1 minus 695 minus 53, so it's 695 by 695 minus 53 by 695. So in this case, actually what they're doing is, this is 1 is 695 by 695 minus, this would be, which is not math, I think. So as you can see, this 1 is, so they have calculated this, so I can show you about. See, this is map 0.076. So now when you subtract the map, this is complement. Okay, so this is minus, again 0.076 is the 53 by 695 in this case. So this is 1 minus the decimal value of 0.076 is just the probability of map. Okay, so now I just hope that you can understand. For intersection, you just have one value, and subtracting the intersection for the union where there is either or. Now let's just move towards the exercise. Okay, so now, okay, I gave you an example of, let's just do one or two questions from there, and then you can just solve these pretty simple questions. Guys, if you see this question 1 now, complete the probability distribution. I'm sure you can complete this. It has to be equal to 1, which is 1 minus 0.1 minus 0.05 minus 0.6 and minus 0.05. This is 0.1, 0.6 plus 0.7 and 0.8. 1 minus 0.8 would be actually 0.2. So you can have 0.2 here. And then this is ACE would mean adding A, C, and E. So it's going to be 6, 7, and 0.9. 0.9. Where E is this. So now you need a union of all this. This is ACE and BCE. So for this, now you already have a common. So you just have it once, but then subtract it. You're adding both of them, but then you have to subtract C and E again. So instead of that, I would just simply write A, B, C, E. So A is actually equal to 0.1 plus B, which is 0.05, plus C and E, which is 0.6, and 0.2. We have Similarly, we have E complement where E is in part B, A, C, E. So E complement would be B and D, 0.1. Okay, similarly is the B part, and now let's just look at this question. Let me just drop this off and see if I can. Okay, I'll just explain to you this question. The die is weighted in such a way that each 2, 4, and 6 is twice as likely to come. So what you're supposed to do in this is just have probability of each usually as 1 by 6. So it's x for each probability, But then for 2, 4, and 6 is 2 of x basically. So you can see that this probability that this is going to come has twice. So it's going to be multiplied by 2 for every x of 1, 3, and 5. So find the probability distribution. So rolling less, this is just a die of rolling less than 4. So you can usually just have, 1, 2, 3, 4, 5, 6. So out of it, this is 1 by 36, 1 by 6 in this case. So now this is 1, and 5 is 1 by 6, but this is actually 2 by 6, and this is 2 by 6. So you can just, this is something which is a biased die. And then in this case, you can just simply add the possibilities, you just draw probability distribution based on this. And then the similar question 1, you just add up the probabilities of each in this case. So 2 by 6, what would be 2 by 6? So less than 4 would be 1 plus 2 plus 3 probability, okay? Now let's just move on to something different. We have similar concepts. Okay guys, this is This is again talking about probability distribution for mutually exclusive and non-mutually exclusive, right? Alright, let me just explain this to you. Determine whether the information shown is consistent with the probability distribution. If not, say why, right? So now probability of A is 0.2, probability of B is 0.1, and probability of A union B is 0.4. Excuse me. I told you that the union is supposed to be an addition of both the probabilities, and then you subtract the intersection from it. So now in this case, you can see this 0.4 is actually greater than 0.2 and 0.1. Now how come is that possible? Okay, so this is not a probability distribution, so I'm just going to put a cross in the first part. The next part says it is 0.2 for probability of A, probability of B is 0.4, union is 0.2. That means this union is actually, should be actually equal to at least probability of A and B, and should actually be lesser than, not greater than, and in this case it's totally less than, at least it should have component of B, it's completely ignored. So again, I would say that this is not a probability distribution. This A union B is way too less than one isolated event of B. So now we have probability of A 0.2, probability of B is 0.4, and intersection is 0.2. Okay, now the intersection would mean that either 0.2 is common, or there are other possibilities leading to 0.2, which is actually within the two sample spaces. This is a probability distribution in this case. Now you can just do other parts, and let me just explain one more part too, where you have 0. Okay, you have a 0 here. Okay, so possibilities 0.1 here, B is 0. Union is actually 0, so this is again not a probability distribution, because you can't have union less than either of the numbers. So because had it been minus something, and probability can never be negative, guys. So now let's just look at other, you can just do these chart questions. Okay, we have 51, this is a hard type question, I think. So let's just look at this one. And this is the last question that I'll be attempting for this lecture and session of today. So question 51 and 52 probably, again, they are about investments. They are the same way. While statistics are not available for web entrepreneurs who fail, the venture capitalists that finance such internet startup companies have a rule of thumb. For every 10 ventures, okay, let's just read the question first. It says, what is a sample space for the scenario? Always read the question first, then read the whole question. You need to know the requirements of this question first. So then you can just go about reading the text. So we have 10 ventures that receive financing, and there are plenty that do not. So 2 will be successes. So what is the sample space? Obviously it has 10 ventures. That will be the sample space in this case. Then you can just explain the sample spaces. What is this sample space S? And S is actually 10. But S would be, now out of that there are plenty that 2 will be stock market successes, okay, and which means spectacular profits, two market successes. Then we have which means spectacular profits, and then 3 will be sold to other concerns. 3 to other concerns. There's this number 5, and which translates into more modest profits, and the rest will fail. The rest is actually 5 will fail. So again, this is going to be modest. Now they're asking you sample space. You have the entire sample space of 10. Associated probability distribution. Associated probability distribution would mean actually 2 by 10, 3 by 10, and 5 by 10 for failure each. What is the possibility? That is, you can just simply say this would be probability of A, probability of B, and probability of C. So what is the probability that a startup venture that receives financing will realize profits for early investors? So now in this case, obviously the ones that will fail are subtracted from the total sample space. So now you have 5 by 10 is the probability that it will realize, because it's modest profits and will realize for early investors. So now it says will be successfully spectacular profits for early investors into modest profits, more modest profits. So if just for early investors would mean that this is 2 by 10, okay, plus we can have for modest profits 3 by 10, okay. So either you just have 5 by 10 or is equal to half, because the rest will fail, or you can just be very simple, explain that this is going to be 2 by 10 or 1 by 5 possibility. So 5, right? So now you can have all these options with you for probability. Now let's just look at this last part, 52, how you're supposed to return this. It is also a similar thing, just talking about trading options, just the same thing. We have 17 or below offering prices. So what is the sample space? You have a sample space of 126 initial public offerings. Initial public would mean that when companies are initially listing themselves on stock exchange, they would be going via the banks. So we are going to be taking them as the primary market. 73 are trading above. So write down associated probability distribution. So it is simply 126 by 126, 73 by 126. 53 that have failed to live up to their first day billings. This is 53 by, and 17 are below offering. 53 have not failed, but they have failed to live up to their fabulous first day billings. What is the probability that an internet stock purchase during the period reported ended below its initial offerings or above the price it closed on its first day? So below it is 53 by 126 and above 73 by 126. Just add them up, but you're not going to be adding this 17. So out of 126, either you subtract the 17 and you get the total value, then you can just simply divide by 126, or just add them up together by 126. So you can also see the example 3, which is a hint to you. And guys, you can do the rest of the questions here, because these are all very similar in concept and techniques. This is example 3. I just told you about this probability distribution thing. Make the probability distribution like this. In the exam, if a question comes to you, what is the outcome? They have given you this is 53, 126, 73. You just divide it by the total sample space and you get the probability distributions. And then you can just add them up if they ask you about the favorable outcomes, or you can just simply take an intersection if they ask you for both this and this, then you will just give one outcome. If they ask you for both, then you just this or this, then you just add them up. So now thank you guys. I'll see you next week. Good morning class, this is your instructor. Today I'm going to be talking a little more about the probability that we were doing in the last class. Let me just brief you a bit about conditional probability, where we have a sample space where there are n number of possibilities. Let's suppose we have 100 possibilities in this case. So whatever probability that we would calculate by looking at how many possibilities there exist for the total sample, then we are going to be considering whatever conditions are applied. So if condition number one could be, let's suppose I am going to be drawing out in a deck of cards, let's suppose 4 jacks. So now you should know that there are 52 cards, and the number of outcomes that you can actually have would be, again, 4 jacks. Out of that could have, now let's suppose you can have as many outcomes as you want, but from a sample space where you can have combination of 4 jacks combined with 2 or 3 cards. So I want to, first of all, wanting to find, you need to draw 4 cards, right? So these are 4 cards, out of which your main target would be to find, maybe jacks. But I do not know whether actually the jack is coming in my, actually drawing out those. So I have to first of all calculate all the drawings from those 52 cards, right? So like I said, the sample space could be 100 from a set of possible solutions. So over here, the sample space could be 52 into 51 into 50, and then could be 49. Divided by, then you can have 4, 3, 2, and 1. Then you can further, make them simplified. So if I want to simplify this entire thing, then I have to have a, let's suppose, calculator with me. And I can just simply multiply them together. So we can have 52 into 51 to 50, and then into 49. So we have, let's suppose, 6497 400 by, then we can have 12 in 44. Then this is 6497 400 divided by 24, and you get 270725. So now, okay, now what I'm trying to explain to you is, first of all, when you're drawing out cards from a deck of cards, so you first of all need to know that there are 52 cards. Now in the books, you're going to be given information about whether it's going to be a game of poker, or you are going to be talking about full house, where you can have combination of at least 3 or 4 or 5 cards, where all those cards will be of same denominations. So now then comes the concept of denominations, so which is actually in the previous chapters, but since I have rather you skip those. So now denomination is basically, in those 52 cards, we can have 13 denominations of 1, let's suppose could be the heart. Then we can have 13 of spade, then, or it could be, the clubs, so we could have the clubs, and then we could have the diamond, and then we could have the spade with us, So it's something like this, then the spade, right? So all these denominations, now out of those denominations, as you can just see simply that, we have 13 into 4, which comes to about 52. So now these are 52 cards, and these are known as denominations, okay? So now what are the basic figures that are in each denomination? So for instance, I have A as 1, okay? Then we have 2, 3, 4, 5, 6, 7, 8, 9. Then we have, jack or 10, then you can just simply say that it's a jack. And then we have maybe 10, or then this is a queen, then there's king. So now you can just simply see which or how many are there, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So now we have 13 cards of one denomination. Then there's a suite, or suite, you can pronounce it as suite. It's written as SUIT. Okay. Now this means basically that we have, okay, so if I want a heart or just a 4, let's suppose. So if I want a heart, then I could have 13 from which to choose. But if I also want to just know about if there is a chance that I can have a 4 out of it. So now 4 can be of each denomination. Okay, so 4 can be of each denomination. So in this case, the condition first of all has to be that there is 13. If I draw 1 card or I draw 4 cards, but whatever the possible outcomes in this case would be, like I said, 100 possible outcomes. So in this case, there could be 13 possible outcomes of, because you have entire denomination of 13. And in those, out of these, then you can have maybe selection of, you want a 4 of hearts, or just simply a number 4. So if you just simply wanted 4 of hearts, then there will be just combination of 1C1, because there's just 1 4, so it will be just 1 and 1, because you'll be having 1 4 of only hearts. And we're just talking about the hearts denomination here. But if I were to just look at, okay, 4 from the 13 denominations, now 4 can be of, from this, and this. So now there are 4 suite in this case. So now you have combination of 4, and then you can just, out of these 4, you can have the possibility of drawing 1. So then this possibility also exists in this case. So now this is the condition that I can apply. So whatever condition then I can have is that there are 4 possibilities of having a 4 from, a suite or suite of 4. Now these are the conditions. Similarly, you can have a condition regarding your performance in the exam. And I could say that there are maybe some people who are going to be excelling brilliantly in their exam. For that, then you can choose yourself as well and choose maybe, okay, I say then there are 2 people who are going to excel. So first could be you. So you can always have 1 C1 in that case, because you are going to be choosing yourself. And the other could be out of those 7 people that are in the class who have appeared for the exam other than you. So that could be now, since altogether there were 8, and you are to choose from a sample of, let's suppose, 2 students. But now these could be all the possibilities that you could have. And then it says, before the 8. So these are all possibilities that you could have. Any 2 students could pass or fail. That is just your conjecture. It's not the actual results. You're just predicting the result that out of 8 students, if you choose yourself, then this is the total. But then if you choose yourself, the remaining are 1. And 1 you can choose from here. So there's 7 into, then you're choosing, so this is going to be 7 in this case. If you put a condition that 1 is you. So basically what we mean by condition is that any kind of exclusivity required of the outcomes in which your desired outcome is meant as a condition, then that is known as a conditional probability, because you are imposing some kind of a restraint, some kind of a constraint on the possibilities that outcomes could actually exist. So all those possibilities are restricted in the domain of whatever condition is there. So there could be at most 2 students, there could be at least 2 students. So these are the concepts of complement. So I'm going to be going towards section 7.4 now, so that I can give you, a countdown of all the possible, situations that you can come up with, and all of the, questions or queries that you can handle. For this chapter, section 7.4, this is probability and counting techniques. The book is Finite Mathematics, and it's by Stefan, Waner, and Stephen Costinoble, 7th edition. I'm going to be switching on to the book now, so that you can just simply look at the examples. So in the next section of this lecture, I'm going to be doing questions. So let's just move on towards now the chapter. Okay, now guys, I've switched towards the section as you can see it. Now, if you just look at the number of favorable outcomes to number of outcomes, like I told you that you will first of all be having the total number of outcomes, okay? So now the total number of outcomes is ns, and then an event could be of your choosing. And this has been inspired with chapter 6. So for instance, like I said, you could have possible number of outcomes. So in this case, it's just a small example where there's a bag that contains 4 red marbles and 2 green ones. Upon seeing the bag, Susan, who has compulsive marble grabbing tendencies, sticks her hand in and grabs 3 at random. So when you grab 3, that means you're drawing 3 out of option of 6. So 4 red and 2 green. So this is the total sample space of 20 possibilities. Then the next part is that you want to choose out of the 4 at least 1, and that would be 4 possible outcomes. Because now out of 6, only 4 exist as red marbles. Then if you wanted 2 green ones, then you could have just, and how many is she drawing? So there could be 2, and so there are 2 further drawings allowed. So you could just have, maybe if you just want both the green, then you can have 2 and then into 2. But since now we are looking at the first step, which is the red marble, so there are 4 possible outcomes. Let's just see what further is there. Now, like I said, that when you choose 2 green marbles, so you have 2 more drawings allowed, because 1 drawing you've already made out of the 3 that were given as a condition to us. So the 2 remaining are of the sample space for the green ones. So the only possible outcome was 1, and you multiply those outcomes, and then you would be dividing that total outcome by the condition that you have, which is the sample space. So for conditional probability, you always divide it by the total sample space, whatever condition has been given to you, which is 1 by 5 in this case. Now let's look at just a lottery example where you have Bank of America, Key Corp, General Electric, Pfizer, Valiant Pharmaceuticals, New York Community, Bancorp. So after downtown stock market means that probably the stock market was not behaving well, and that it was bearish perhaps. So you decide to ignore your broker's cautions, and now basically you have to select 3 stocks from possibility of 6. So in this case, what would be your sample space? So if you question yourself before looking down, you can just simply see that you need 3 drawings, and out of a sample space where you have 6 options. So 6 options, combination of 3 drawings, so you have 6C3, and then you can just simply have 6 into 5 into 4, and then you can have divided by 3 into 2. So you have 20 possibilities, because 6 into 5 into 4 by 3 into 2 into 1. So 3 into 2 is cancelled by 6, and 5 into 4 is left. So as you can see that this is okay, 6C3 would be 20 possible outcomes. Now the next part is a bit tricky. So where they ask you that you purchase BAC and Key, which is Bank of America and Key Corp. So in this case, now you already know that there are, out of 3 choosings, you have already chosen 2. So there is now the third combination would be Bank of America, Key Corp, General Electric, one combination. Then Bank of America, Key Corp, Pfizer would be the second combination. Bank of America, Key Corp, Valiant, third combination. Bank of America, Key Corp, New York Community Bank Corp would be your fourth combination. So in this case, that means that other than these two out of 6 minus 2, you have 4 more options from which you will choose one more stock because you've already chosen 2 stocks. So 4C1 would be your further combination possibility to draw one more card from the remaining possibilities to have all collection of 3, right? So in this case, 4C1 would be 4 because you just expand it just one time, so it's just 4. And then you have 4 by 20, which is the possibility where you can have, like I told you, back key, Pfizer, back key, Valiant, bank key. You have General Electric and New York. So there were already 4 outcomes: 1, 2, 3, 1, 2, and this is 1, 2, 3 again. Second outcome, 1, 2, 3 again. This third outcome, and 1, 2, 3. This is the fourth outcome. So you can just draw them and you'll know that there are 4 outcomes. So 4 by 20 is 0.2. Now B part is that you need to select at most 2 of the stocks you purchase decline in value by more than 2.5%. Okay, so first of all, the easiest part is to usually go by the complement approach, which means that for at most you would have the exact opposite as at least. At most is like the maximum, and at least is like the minimum, right? So at most 2 of the stocks would mean that for at most either 0 stock, 1 stock, 2 stocks, right? But at least would be all 3 stocks. So for all 3 stocks, you would know that if they are to be less than or by more than 2.5% declined, then you can just say that it exceeded by 2.5%. So you can just simply, from the sample space of 20, 3C3 combination would be given by one possible outcome because they would be cancelled by each other, and you have the opposite, exact opposite, because all 3 combinations from all 3 would be just one possible outcome, that all 3 are not declining in value by more than 2.5%. In this case, that would be just the exact opposite of this. So you can subtract that complement from 20, you get 19 by 20, so that would be the answer. But the second alternative, they have been given a few alternatives to us, right? So they have been given, I guess, the first alternative would be that first of all you find out what is the sample space in this case, that if you assume that at most 2 stocks decline in value. So if you look at this one, you get the sample space first of all, calculate it, and then you calculate it. So this now, like I said, there is one possibility: none of the stocks decline by more than 2.5%. So why is that we have taken this alternative 1 as none of the stocks? Focus to say at most 2 stocks declined. So that means either 0 stock declined, 1 stock declined, or 2 stocks declined. So you have 0, 1, 2 for at most 2. So that means, just like you say, at most 2 heads in a set of 3 tosses of coins. So you can have either all tail and no head, because you said at most head. So by the same argument, there could be no stock that declined in value. So you can have, in that case, first alternative, as none of the stocks that declined in value, choose 3 stocks. Then this is one possibility. Then alternative 2, you have 1 stock declined and it would have 2 steps. Why? Because 1 stock declines and remaining 2 do not decline. So if 1 stock declines, then you can just simply have out of 3 stocks, 1 that declines, 3 possibilities, 2 that did not decline, that would be 3 stocks out of 2 that did not decline, 3 possibilities, and again you multiply, that would be 9 possibilities for this alternative. The third alternative would be 2 stocks that declined in value and 1 stock that did not. Okay, so now you see 2 that declined in value but 1 that did not. So you get my point, right? So first of all it was 0, at most would mean 0, 1 and 2. So 0 stocks, that means none of them declined. Second alternative, 1 stock declined, 2 didn't. Third alternative, 2 stocks declined and 1 did not. And again you have 3C1 and 3C2. So you just multiply the possibilities for each alternative. So you have 3 into 3 and then you add them all up because there is an OR. So 1 alternative plus 9 possibilities for the second alternative and 9 possibilities for the other one. You have 19 possibilities. And then you can just simply divide it by 20, or you can just take advantage of whatever I told you about the complement process, that you can have one possibility, the opposite, exact opposite of it, and you can have 19 as we calculated above. Now again, the deck of, this is a poker hand, right? So for poker hand, you have 52 cards, and you are given 5 out of it. So you choose 5, so you just simply 52, C5, because it's random, it's not in an order, so you have 52, 51, 50 into 49, 48. So it's 52, 51, 50, 49, 48 divided by 5, 4, 3, 2, 1. And you get the answer of 2598, 960. Okay, now they have given you a condition in this, they ask you to calculate a decision algorithm. So decision algorithm would be where they have asked you for the probability to have a full house. So now a full house, they've already told you that this is 3 cards of one denomination and 2 of another. So since we have picked 5 cards, so we can have 3 cards of one denomination. I told you there are 13 denominations. And out of those 13 denominations, possibility is again 13. And then for each denomination of 13, you have 4 suites or 4 suits. So now, if you have 4 suits or suites, that would be club, heart, diamond, and you have spade. So those 4. And out of those 4, you can have, for the first choosing, because that is our first denomination, we can have 3 cards because we want the 3 of the same denomination. That's why we're multiplying it with this 13. 13 of the same denomination, but we would want that there are the cards, 3 cards of that denomination. Okay, so now, so since we know that there are at least, there could be occurrences, 4 kinds of occurrences within 52 cards of 4 types. So there could be a possibility that out of those 4 types, there could be 3 cards chosen over the first denomination at that time. So the concept is that the first time that we take out a card, we are given 13 denominations, and out of those 13 denominations, we have 4 of clubs, spades, hearts, and then out of those 4, 3 cards we can have of that particular denomination that we want, of our choosing. What is the possibility? So possibility can exist with the same denomination, but since we want 3 cards, so we can have, out of the 4 possibilities that we can have for the same number. So again, then we have second round of denomination. So since we have already, chosen the first time around, now then again we will be using the second time round. The second time around when we use this would be again 12, because notice we say that consists of 3 cards. So we have, now out of those 3 cards, second round of denomination would have 1 less, because now we have chosen of 1 denomination. So get this point, there are 4 denominations. Out of those 4 denominations, we choose 1 card. So naturally, the denomination would reduce to 12 cards. And out of those 12 cards, again, there's a possibility that there are 4 options still available to us from other denominations that are interacting with 52 cards. Randomly drawn, then we can have 2 cards of that particular denomination. So you have to really look at this and the form of denominations and suites. So we multiply these possibilities together. Okay, so now since we have, let me just revise that for you. 5 cards, 3 of the same one, and then we can have, like they said, 3 cards of one denomination and 2 of another denomination. So then, since we have 13 cards, because none of them was taken at that time, there was 13, and then this denomination, the denomination's second time we take, now we are given an option of 12 because one card has already been taken. So again we have 2 cards out of the possibility of existence of 4 of each type, and 4 of each type, and we have 3. So we have full denominations. So you multiply this together. So 0.14% chance that you will be dealt a full house. Again, you have more poker questions here. You have to find the probability that you end up with a full house. So again, you have to basically exchange 2 cards, club and spade. So you already have one missing club, spade, club jack, and you want to also replace them, remove them, and then you can have. So there are different possibilities. If you want to end up with a full house, so at least you need to have 3 of one combination. So either you could have these 10s and 2s removed, like they have mentioned here. You can have a denomination other than jacks, 2s and 10s. Jacks, 2s and 10s, if you remove from 13 denominations, 13 minus 3, jack, 2 and 10. So then you could have 10 left. So 10 possible outcomes for 10 denominations when 3 have been removed. Because you have 3 and then you have 2s and 10s, and you don't want 2s and 10s in this case, that's why. So you remove those denominations. So out of choosing of 4 types of sweet or soup, now you select 2 cards. That is when you don't want these jacks, 2s and 10s. Or you would want out of that either 2s or 10s. Okay, so now you have, there is a possibility that either you choose 2s or 10s. So there are 2 denominations, sort of like if you have 10 options in 13 options in one denomination, you subtract 3, you get 10. But if you just 2 out of those denominations, so you just have sample space of 2C1. And then you would be selecting 2 of theirs when you have, now of that denomination only 3 are left because 1 you already chose. So now in this case, if you just see that you have 1 of each denomination of jacks except for 1 of clubs. Similarly, you don't want, if you choose 2s and 10s, then you have this total sample space of 2C1. And then you can have, since you already have one denomination with you of clubs and spades, so now whatever denomination would be less of these 2 denominations, because you're choosing 2 and 10 in this case. So there will be 3 left out of the total denominations of 4. Again, let me just revise this. 4 at this time, because we were not having these 3 denominations, you had 4 other numbers like A, King, Queen, 3, 4, 5, 6, 7, 8, 9, and you did not want the jack. So you have 10 and then 4 of each others, and then you select 2 out of that. Or you have just jacks, 2s or 10s, sorry, and you have 3 out of the 4 because you already have the 2s and 10s of other denomination. Like you have 2 of clubs, you can't draw that. So now there are just 3 more sweets or suits left for the 2. There will be diamond, the heart, and the spade. Similarly for 10, all others except for spade would be left. So you have basically 3 to choose from. 2 cards, so you have 66. Now how come 66? So since we have an OR here, we have a union, so you add them. So now it's 10 in C1 into 4 C2. So that would be 4 into 3 by 2. So that would be 6 basically. 4 divided by 4 into 3 divided by 2. So 2 will be cancelled, and there will be 6 remaining in the numerator, and you multiply it with 10, you get 60. And in here you have 2, C1 would be 2 into 3, C2 would be actually 3. So 3 into 2 would be 6. So 60 plus 6, you get 66 in this case. So you have 0.0611. Now in the second part again, they've asked that, since there's... Okay, so now let me just also tell you that when you draw the 5 cards, you had 47 cards left. But in part B, they're telling us that you end up with 4 jacks. So you already have 3 jacks. So the possibility of having one more jack is 1C1. And if you remove that, how many remaining are left? 46. So now in case you see 46 cards left, and 1C1 is removing the jack of clubs, which is missing in this case. So 1 card from the remaining 46 cards. So the total outcomes is 46. So 46 by the total sample space of 1081, and this sample space was, as you can see, it's the total sample space of having 47, and sample space would not change in this case because you're selecting, the 2 cards. So now, if you can just simply, because you're dealt with 2 of a kind, so you just want to replace these cards. So the possibilities that you have is after those 52, after you have the 5 ones. So you have 47. So out of 47, 2 you have the sample space of 1081. So as you can see, this is 1081. And this is the same sample space where you again have 1 separated, because you're just going to be choosing that out of a possibility of just 1 jack left. Had it been all jacks inside this, then it would have been a possibility of 4C1, because you draw 1 out of 4, not just draw 1 out of 1. So just 1. And then you have the union of if both of the events occur as either or. So you just add up, and since perhaps there's you can have an intersection if it's possible, but you just simply add them together, because there's a null set, because totally different conditions. One is where this jack of clubs is missing, and the others are where you are trying to replace 2s and 10s, or you are going to be having reduced the denominations from 13 to 10 for all the jacks that you have there at that time. So you have 3 jacks, so you have or you just have already, as you can see, jacks, 10s and 2s. You don't want those. So you have 13 minus 3 that you have. So you don't have any intersection in this case. You just union, so we'll be just adding 0.0426 plus 0.0611. Now let's just look at this committee where you have an option to include a candidate. Now like I told you that there's an association. So if you're given a question where you are, okay, let me just read this out. You are an undergraduate student, even though you are not an elected student senator, you would very much like to serve. So senators at large as well as student government delegates are chosen by means of a random drawing, so you already know that there's combination. 30 undergraduates for the position of senator at large and 6 for student government delegates, and you have been offered a position of student government association. 6 government delegates, so you have a government association by the president, so happens to be a good friend, so you wish to join it. So if you have such positions or such options where you are considering yourself, so you would be subtracting 1 out of the total possibilities that you have. So in this case now, there are 13 undergraduates for position and 6 candidates, and you have been offered a position, and then it has not been explained whether this includes you as an undergraduate student, and you're not elected. So and now it says they have, okay, now if you want to determine whether they have elected you or not, you just have to just see what is the condition in here. So it says that there are already candidates for the position and you are not elected, so that means that you're going to be adding yourself first of all to the sample space. Plus 13 plus 1 would be have 14 for undergraduate positions. The sample space is a set of all possible outcomes. So for this you have now how many positions? Now let's just look at this. One option is to include your name on the list of candidates, and the option second is to join the students and add your name to the list, right? So now you are to make how many drawings. Now this also depends upon what they're asking here. So if they say that the student affairs consists of one elected faculty senator, one faculty senator, one elected student senator, 5 student senators at large, 2 delegates from student government, the president association and the president of graduate associations. So all in all, they are asking that the result is 14 for 4 undergraduate positions. So each outcome consists of a set of 4 lucky students chosen from 14. Okay? So now how come they're asking you? So you have to think over it, right? So I think that you have thought enough over it. So actually this basically means that you include yourself in the graduate position of 13, and there are 6 candidates for 1 delegate position, and alright, they have not clearly mentioned in this that whether how many students they are choosing. So since this is an example and they have already mentioned to you in the solution, so what you should, in the exam, if such a question comes to you, you would know that you would be given the number of drawings. So let's just assume here that they have given a possibility of 4, which are to be selected from the undergraduate students position. So in this case you have 14C4 as a total sample space. So first of all, like I told you, you have to subtract yourself from the position in which you are considering yourself. So you have 13 graduates and 3 are the choosings. Similarly, you choose yourself, so there will be a combination of 1C1 in this case, right? So this is the first option for you because you have been given the option either you choose yourself from the 13 remaining, because this was the first condition that there are 13 candidates at large for the position of senator and 6 for the student government delegates. And if you're considering yourself as the delegate, then you have to again subtract yourself separately, just this as 1C1 and 6C1, because now why is that we are taking 3 remaining from here and you choose yourself 1 from here. And in the second part we have 7 candidates from which 2 are selected, okay? So this is the second option that has been given to you as part of the question. And in this case, you have to know that you did not initially include yourself in this condition that was applied. So the condition was that there were 6 candidates and you were not elected. So when you add yourself, then there are 7. And the option that they have given to us in this is that 2 are selected in this case, right? So that is the total sample space. So when you are choosing yourself out of it, you have 1 to choose from and then 61. Let me just revise this to you. The University Senate bylaws at Hofstra University state the following. The student committee shall consist of one elected faculty senator, one faculty senator at large, so there are two. This is the third one, and then one selected student senator and 5 student senators at large, including one from graduate studies. So that would be 5 separately. That is a position, and 2 delegates from student government, from student government association, president of government association, and the president of graduate student organization. It shall be chaired by the elected student senator on the committee, and it shall be advised by the dean of students office. So you are primarily given an option where there are 3 undergraduate candidates. You are not elected. So you have been offered a position because you happen to be a knowing person who is in charge of allotting those positions well. So there are 13 undergraduate students, so if you include yourself, that will be making you as 14 for the position of senator at large. And 6 candidates for student government delegates. So if you include yourself inside, like I told you that when you include yourself, so you have to take out separately the possibility of yours and the other one. So there are 7 candidates together in that case. So for the first option, 1 is to include your name on the list, and option 2 is to join the Student Government Association. So there's a 14 undergraduate students if you include yourself, and then the option, as per the option 1, 4 positions for 4 undergraduate positions. So for 4 undergraduate positions, for 14 undergraduate students, there are 1,001 outcomes that are possible, because all these could be shuffled because they're selected randomly if they're chosen. Any 4 could be lucky from the 14 set. So you choose yourself as 1, and then you remove that possibility from 14 and 4. So you have 14 minus 1,